Hello, my name's Chris Kurzik, and I'm the Principal Engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Welcome back. In this program, we're going to dive into example 3, and we're going to begin with a mode confirmation. So we'll review all the different modes to make sure that we've got we're building the right model. And when I do an analysis, we always make sure that we've got all the variables correct because it can change the answer a lot. We talk about histograms and how to build them and what's involved with that. It's a key part of creep assessment modeling, and it's important to understand, the how it affects the precision of the calculation. Secondly, or the thirdly, we're going to look at thin wall calculations because the specific example that we're going to use utilizes the thin wall calculations. And last of all, we're going to stop with some conclusions. Okay, in this example, this is a crude heater temperature excursion. We want to determine how much damage occurred to the tubes. Are the tubes okay the way they are now? What's the remaining tube life in this unit? And the reason why we would need to know that tube life is for turnaround planning. Is it good for, this month, or is it past? And these are the very important considerations for planning, of course.
Start with the table 2.2, the flaw assessment, to evaluate, to make sure that we're covering all of the right elements of this situation. So we have a crude heater. It's a boiler component, horizontal style, cabin style. Tubes are horizontal. Its design is Section 8 Division 1, post 1998. Materials of constructions, SA335 P22. And the temperatures are here, and because it's a fired heater, it's a matter of operating hours, not cycles of operation.
Double check everything and formalize it. That's why I'm a big fan of table 2.2. So in here, do we have a brittle failure issue with running lower than the temperature as per part 3? No. Do we have any excessive scale? The reports say that there is just a light thickness loss. The part 7 says we check for blistering, which is very common with furnace tubes. No bulging was noticed. Part 10, this is where we have issues. High temperature excursion inside the fire box. Tubes, bends are outside the box. So this is important because we don't need to really look at the tube bends because they're outside of the box. They're considerably, they could be a lot cooler because they're exposed to the outside air and they're not to the actual environment. Of course, this is up to engineering judgment as well because the tubes are still hot. But anyways, we also look at to see if there's any kind of damage, gouging or dent gouges, and we didn't find anything. Of course, that would affect the assessment of part 10. And in the previous videos, we talked about the different types of modes and the combination of modes, and that will determine which one we're going to use. It's also important to take a look at the internal environment. In this case, it's just crude. But there are other considerations that, like the level of chlorides and other issues that may cause the failure to increase. Now let's look at the inspection history, repair history. This is always quite difficult to get, or not always, but it's important that the inspectors are conversant in API 579 and understand the requirements for those reports, because it's really everything with doing a level 2 assessment. So this is as far as we know, this is the first excursion into the creep range of the component. Whenever we do reports, that we spend a great deal of time really explaining, our assumptions. And because again, it throws off the entire calculation if there's something we don't know about. Operation history: the vessel was placed into service 2000, and they performed inspections every 3 years. There was no repairs required, so it maybe the turnarounds were every 3 years. That would be probably a reasonable guess. Now, if we interview the business people, we can look at the future anticipated operations based on the retirement calculation. If they were just looking at the straight corrosion, they would expect a equipment lifespan of 2026. And in the time of the calculation, this was 2020. So we're looking at about 6 years. So at that point, the vessel would be replaced, and unless the business plan changes, and this assumes that there's no deviations from the original design parameters. If they decide to run at a higher temperature or different kind of product where there's the pressures change, or they want to run it to a point where the unit begins to the pressure drop gets higher and higher, then that has to be assessed.
Go through our material data. So we've got P22 material, which corresponds to, by definition, a 2.25 chrome 1 moly. We need these properties to continue our example later, because of course, when you add alloys to materials, the properties change. The material's annealed. It's an 8-inch pipe, so therefore the diameter corresponds to 8.625. Schedule 40, there we go. And it's a seamless pipe, so our joint efficiency is 1. We have a unsupported length of 144 inches. And basically, if you want to superimpose that, you just use like beam theory. And if there's any interest in that, we can do a future video and add that to this example. It's a cylindrical shell, so that's important in the calculations. And the future corrosion allowance is 0.1. Inputs, we've arranged the data so that it's more easily manageable. We have our pressures haven't changed. They were sitting at 210 psig. Our temperatures, our past operating is 1115 Fahrenheit, and you can see here very clearly what the temperature excursion was, and a past operating history of 131,000 hours of service. And excursion that occurred was 336 hours long, and we're hoping to get to another 43,000 hours out of the unit.
Now let's jump into steps 2 and 3. Determine the load history and assessment temperatures. Now this is the part we talked about, histograms and the development of that. And so basically this is a snip out from API 579, and this is basically a temperature, pressure, corrosion rate on the vertical axis, and on the horizontal independent variable, which is time. And you can see that this is the different operating parameters. And of course, these lines are could be considerably more confused. They could have a scatter plot and so on. So it's important to sort of try to normalize this plot to really understand it. And in this case, we've basically got 1, 2, 3, 4, and 5 different zones that we want to look at. So what this in the level 2 assessment, they basically break those down into, they simplify it into a model, which is a sort of it's a step model. And this is an idealized parameter. And of course, as you get more and more detail, you start to approach the exact curve. But in a level 2, you're approaching it, but you have to be aware that it's not an exact. And so we break these down into discrete groups in order to make a decision about our assessment. So in step 2, we were focusing on the variable they call M, and that's the typical condition. So again, we have step 1, the past performance, 2, the past excursion, and 3. And you can see how we've organized this, and it's starting to take the shape of a histogram. The second one is the assessment temperature for time increment NT. So this is called a sub increment, and this is for N. So in this operating case, we've developed 2 sets of data, and it depends on your model. You may have more than 2 sets for this. But in our case, we're using 2, and we're using 2 for the past excursion and the future as well. And you can see that there's pressure, there's the service temperature, and the design. The design, actually, this should be more like the operating temperature, but you can see that we're in case condition 1, we are within the zone, and you can clearly see that in the past excursion what the temperatures were and the amount of service time it was in. And now we've got data that we can plug into spreadsheets, and it's super clear what we're trying to achieve. So we're going to move onward to step 4, where we determine whether thin wall stress theory or the thick walled stress theory applies. And if you looking for more definition of that, you can go to paragraph 10.5.2.5, and there are definitions in 579. 579 is really awesome. It's a very well self-contained document. So in this case, I've simplified this here. Again, please read the document, but if we have an 8-inch pipe, it's the thickness is shown, and basically where our ratio is 26 and we're greater than 6. So we've confirmed that we're going to use the thin-walled stress theory calculations. So now that we've established M and N, as before, we've developed our histogram, we can start to dive into our calculations. And in addition that we used table 10.2 thin-walled shell calculations, and the sections from each edition of 579 must let you know that they have changed sections. And so, but you still have to look at both to make sure that there's been no changes. So I used the 2007-ish version. And so first of all, we do the first calculation where we take the mean diameter, which is the average through the wall, and then we take the T of the component, And we have to look at each type of component. So if you've got a different components in there with different diameters or wall thickness or materials, you have to assess each one differently. So in this case, we have the past operating, the extrusion, and the future. So we did this calculation and we determined the stress. And then we took the mean stress, okay, and then we based on this calculation here, we determined that principal stress. Onward, we looked at the other modes and we didn't find anything appreciable because in this model we're not considering the bending of between the supports as an issue. We're assuming that the supports are well supported, but if you do, then you would have to consider that in your calculation. And of course, this is just principal stress theory. You can do quite a lot for that and build a more complex model. And then from here, you do your final calculation and you get your value for each component. And then you resolve all these components and then you get your stress. Now that we've done all of these calculations, we've determined our stress and PSI, we can go and check compared against the factor of the yield strength. For austenitic stainless steels, they have their own criteria, and for our case, we have like basically carbon steel. So we will be using this to compare against, and it's basically 75% of the yield strength of the material. And be careful to make sure that it's the yield strength at that temperature. And as your temperatures, of course, there's a plateau, but then your temperature, if your temperatures get high beyond your material grade, which is found in ASME section 2, you can go ahead and double check that because your yields might drop. But in our case, we're okay. We've got a material operating in the range. So we've determined to be 11, and it passes because 11 is greater than basically 3,900. And so the first step 5 passes. In step 6, we're looking at the classical principal stresses, and strength of materials people will definitely recognize this equation, and we basically resolve all of the component stresses into a final stresses, and we get this factor here. Once again, we're using the same tables and we pass. So what does this mean? This means that the unit has not failed because we're within the allowable stresses, and so there was no damage done at that point. So what can we conclude so far? Well, we did this level 1 assessment in the earlier examples, and we found it failed and it required to go to a level 2. So the level 2, it passes the condition, which means, was the tube damaged in service to a point where, it needs to be replaced right away? Well, it doesn't need to be replaced right away. So in order to determine how much life is left, then we have to dive into other models. The most famous model is called the Larson-Miller parameter. There's a few different variations of that. There are about 4 to 5 different models in API 579, and there's also more in industry as well. And this will help. This is the $1,000,000 question, right? Is how much life do I have in the tubes? And this will be in a future video. We will continue our studies at that time. I hope you found these videos interesting.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.